Hi, I'm Todd. In many real-world applications, functions cannot be defined in a single closed form. It's often convenient to define functions in pieces. In this section, you'll learn about piecewise defined functions. So let's begin by reviewing the objectives. Evaluating and graphing piecewise defined functions, the greatest integer function, the absolute value function, and equations and inequalities involving absolute values. Now, the U.S. postal rates are a good example of a piecewise function. It costs 34 cents to mail a letter that weighs more than 0 ounces, but not more than 1 ounce, and it costs 55 cents to mail a letter that weighs more than 1 ounce, but not more than 2 ounces, and so on. And so we can define this function as follows. So 34 cents for a letter that is more than 0 ounces but not more than 1. 55 cents if the weight of the letter is greater than 1 but not more than 2. 77 cents if the letter is greater than 2 ounces but not more than 3 ounces. 94 cents if the letter is greater than 3 ounces but not more than 4 ounces. And $1.21 if the letter is greater than 4 ounces but not more than 5 ounces. Now, in this case, notice that each piece of the function is a constant. And so this particular type of piecewise function we call a constant piecewise function, or a piecewise constant function. Let's take a look at how we might graph this function. A letter that weighs greater than 0 ounces but not more than 1 ounce is going to cost 34 cents. So we want to put an open circle on the y-axis here corresponding to 34 cents in that case. And then over at 1 ounce, we'll put a closed circle because a 1 ounce letter is going to cost 34 cents. And all the possible weights in between will also cost 34 cents. So we'll draw a line segment between those 2 points. Now, after 1 ounce, the price jumps to 55 cents. So we'll go up here to about 55 cents. And I need to put an open circle up here because certainly we don't want to, we wouldn't want to have a 1 ounce letter both having 2 different prices. So a 1 ounce letter goes for 34 cents, not 54. But if it weighs just a little bit more, then it'll go for 55 cents. 2 ounce letter will also go for 55 cents. So we'll indicate that with a closed dot. And every letter in between will also go for 55 cents. So we connect those two with the line segment as so. Now, the next price jump is up to 77 cents. So we'll go up here to about 77 cents and put an open circle above 2 for that one. And letters all the way up and including 3 ounces will cost 77 cents. So I need to put a closed circle here and connect those two with the line segment. Then we go up to 94. That's right about here. 4 ounce letter will also cost 94 cents. So there's my closed circle. Connect those two. And finally, the next jump is to $1.21. That's right about here. So I put a open circle there. And a 5 ounce letter also costs $1.21. And all the weights in between also cost $1.21. So that's what the graph would look like. Now, notice how this graph kind of looks like a staircase. And so we call this type of a graph a step, or a function represented by this type of graph, a step function. Now, also notice that each piece of this function is a constant function. And so we refer to this as a piecewise constant function. Okay, let's take a look at another function defined piecewise. And in this case, the pieces of the function are linear. Use f of x to complete the following. F of x equals x plus 1 if x is greater than or equal to -5 and less than -1, and negative x if x is greater than or equal to -1 and less than or equal to 4. Here's what we're asked to do. We're asked what is the domain of f, to evaluate f at x equal -2, 0, 1, 3, and 4, to sketch a graph of f, is f a continuous function, and find all x values where f of x is equal to -2. So we'll start with part A. We'll find the domain of this function. Now, the function may be defined in pieces, but if you notice, if we go back and we look at this function, when the x values actually start at -5 and they go all the way to 4. So in this case, the domain of this function would be any x value from -5 to 4, including -5 and 4. And so we can write the domain as follows. D, or domain, equals the set of x values such that x is greater than or equal to -5 and less than or equal to 4. So there's the domain of the function. Now in part B, we're asked to evaluate the function at some different values. So for f of -2, we have to remember that the function was actually equal to, I'll go back and look real quick, the function's equal to x plus 1 when x is equal to -2. And so here we would have f of -2 would be -2 plus 1 or -1. Now f of 0, again we'll go back to the function real quick here and look, where is 0? 0 is on this interval, and so for that x value, f of x is equal to -x, so f of 0 would equal -0, which is of course 0. And for f of 1, again, that's equal to -x, so that would be -1. And f of 3, on that interval again, we have -x or -3. And finally, f of 4, it's the very last value in that interval, would also be equal to -x or -4 in this case. Now, if we want to draw a graph of this function, we can do so using our graphing calculator. And this problem is a little different than some you might have graphed in the past, because we actually want to only show the pieces of the linear parts of the function for which the function is defined. So let me show you how you can do this. Now, we know we're going to have to enter the function under two different y1 and y2 values, or two different places on the calculator. And what we can do is we can enter the first part under y1, and that would be x plus 1. And we can enter the second part under y2, and that would be -x. Now we still have to do something about these domains. So we know the domain of the x plus 1 part is starts at -5 and it goes to -1. So what we can do here is divide by the following quantity. We'll say if x is less than or equal to, I'm sorry, I should say greater than or equal to there. If x is greater than or equal to -5, or if x is less than -1, and that's what I'll put in this part. And then down here, the domain for this part is from -1 to 4. So what we need to say here is that if x is greater than or equal to -1, or if x is less than or equal to 4. And let's see what this graph looks like. I'll show you my window. I'm using a window from -5 to 5 on the x scale and -5 to 5 on the y scale. And I'm actually glad I looked at that, because I don't think I want my y scale to be 1,000. So I'll change that to 1. Now let's take a look at this graph. All right, so that's what the graph would look at like. Now, in part D, we were asked whether or not the function was continuous. And in this case, if we look at the graph, we can see that it's not continuous because it has a break in it right at x equal -1. Now, in part E, we were asked to find the values for x for for which f of x is equal to -2. And I can also answer this question using my graphing calculator. What I'm going to do is graph the horizontal line y equal -2 along with the graph of f of x. And this is what it looks like. Now, the x values that are solutions to the equation f of x equal -2 occur where the graph intersects that line. And so we can use the intersect feature on the calculator. So I'm going to press second trace, and choice number 5 is intersect. And it's asking me what the first curve is. So let me see where my cursor is here. There it is. So there's my first curve. I'll press enter, and then I'll arrow down to the line and press enter. Now it wants me to make a guess. So what we can do is just move the cursor over there close to where we think that intersection is. And when we press enter, we see that we get an x value of -3, and that is one of the solutions to that equation. Now, the other one's over on the other side. So again, I'll use the intersect feature on the calculator. So I'm just kind of scooting it over there. If I go second trace, choose intersect, I need to move my cursor over onto the next part of the graph. Now, this is one thing to keep in mind. I have to actually physically move my cursor over to the other side of this graph, because remember that we entered this function in two pieces. And notice what's happening here is as I move my cursor around for these positive x values, it says y doesn't equal anything. And that's because if you look at the very top of the calculator there, it's still on y1 because my cursor is tracing on the y1 graph. So if I hit down arrow, notice it jumps now down to the next graph, and now it says y2 up there, which is actually the curve that we want to use. So I press enter now, and it jumps to the next curve, which is y3 equal -2, and that's correct. So I press enter again, and I'll move it over close to where I think that intersection is going to be, and I'll press enter, and it'll give me an approximation for the solution. So the solution is x equal 2. And so there are two solutions to this equation, x equal 2 and x equal -3. Now, another common piecewise function is the greatest integer function. So let's take a look at this function, the definition of this function. The greatest integer function, f of x equals, and this is the notation we use, is the greatest integer less than or equal to x. So let's take a look at how we might write this function as a piecewise function. So if we look at 0, the greatest integer function will equal 0 on this interval because, of course, the greatest integer less than or equal to 0 is 0 itself. And for every other x value up to 1, we'll also have 0. And when we go to 1, though, the greatest integer less than or equal to 1 is 1. So the function will jump to 1 now. And for every value from 1 to 2, it'll equal 1 until you get to 2, and then it jumps to 2, and so on. Same thing in the negative direction. So that's how we would write the greatest integer function as a piecewise function. Now let's take a look at how we might graph this. And again, we'll use our graphing calculator. I have to go back and clear out these previous functions from that previous example. Now, the greatest integer function you can find under the math menu over under the number menu. And choice 5, int, is the greatest integer function. And so we say int of x when we want to draw the greatest integer function for x. And we'll do this in a standard window. Now, actually, I think I'm going to use a window, the same window I used before. That should work fine. So if I hit graph, that's what the graph looks like. Now, this isn't really what the greatest integer function graph looks like. And the problem here is that my graph is actually in connected mode. So if I go back under the mode menu here, and I go down and look at this part of the menu where it says connected and dot, if I want the graph to look appropriate, then I need to put my calculator in dot mode. So once I do that, if I go back and I look at the graph, now the graph looks like it should look. Those pieces where it was trying to connect it aren't actually there. So we can say the greatest integer function is a piecewise function, and again, it's another example of a step function. Another function that we can define in a piecewise fashion is the absolute value function. So here's the absolute value function defined piecewise. If x is less than 0, then f of x will equal negative x, and that's because, of course, x values less than 0 are negative, so we need to take the opposite of them to make them positive. And the absolute value function will be x if x is greater than or equal to 0. So let's take a look at an example, and here we're asked to graph y equals the absolute value of x. So if we go back to our graphing calculator and input the absolute value function under y1, we need to go to the math menu, over to number again, and first choice is absolute value. Press enter. We want the absolute value of x. And this time I'll draw this in a standard window, so I'll use the zoom standard feature on the calculator. And this is what the absolute value function looks like. Now, another important skill is solving an equation that involves an absolute value. And there's actually a process we can use to do that. And here's a part of it. We need to know what to do when we have an absolute value equation. And if we let k be a positive number, then we have the absolute value of ax plus b equal k. And this is equivalent to ax plus b equals plus or minus k. So sometimes we talk about being able to remove the absolute value bars by considering plus or minus k. And we can use this idea to solve equations that involve absolute values, as in this next example. Here we're asked to solve the equation absolute value 2x plus 5 equal 2, graphically, numerically, and symbolically. So we'll start with the graphical part here first. And the way I'm going to do this graphically is I'm going to look at both sides of the equation. And I'm going to draw the graph of y equals the absolute value of 2x plus 5 and the graph of y equal 2. And we're going to use that idea we used before and look for the place where those two graphs intersect. So let's do that right now on the calculator. So the first thing I'm going to enter is the absolute value of 2x plus 5. So there's the absolute value, 2x plus 5. And down here I need 2, so I'll enter a 2. And I think that we can use the same window. So I'll just hit graph. That looks okay. Now, what we want to do is find the intersection for these 2 points. So I use the intersect feature, second trace. Choice number 5 is intersect. And I'm going to find the one on the left first, so I'll kind of move my cursor over here in that vicinity. Press enter to select the first curve. Press enter to select the second curve and move the cursor over close to the intersection. Press enter again. And it's telling me the intersection is at negative 3.5. So that indicates one solution is x equal negative 3.5. So let's go over here and find the other solution now. So I can scoot my cursor over close to that other intersection point. And second trace again. We want to find the intersect. So let's see. There's the first curve, second curve, and I'll move my cursor down close to the intersection, press enter. And it's telling me the intersection for the second solution is at x equal negative 1.5. So those are the approximations for the solution. Now the next thing we want to do is find the solution numerically. And we can use the graphing calculator to do this as well. And what we'll do is we'll use the table feature on the calculator. First thing we want to do is to set up this table. So I'll go to second window, which gives me, let me try that again. There we go, the table setup window. And we want to start our table, in this case, at negative 4. So I'll type in a negative 4 there. And we want to increment by 0.5. So I'll change delta table to 0.5. And I'm going to make this auto because I just want to look at the table in this case. Now, if I press second graph, I'll get the following table. Now, in order to find the solution numerically, what I need to do is to come down here and find where y1 and y2 are equal. Notice in the y2 column, every value is 2, and that's because that's the constant value function 2. And over on the under the y1, we have the absolute value, the values for the absolute value function. So notice that the row corresponding to x equal negative 3.5, we have 2's in both under y1 and y2. And if we scroll down to negative 1.5, we also have 2's under y1 and y2. So again, that's another way to determine the solution numerically. We can also find the solution in this case symbolically. And we do this as follows. Now, I'm going to rewrite the equation on here. So we had the absolute value of 2x plus 5 equals 2. And what we need to do is we need to remove these absolute value bars. And the way we can do that is we can recall that an equivalent equation would be 2x plus 5 equals plus or minus 2. And then I want to separate that into two separate equations, which would be 2x plus 5 equals negative 2, or 2x plus 5 equals 2. I'll focus on this side first. I want to solve this equation. So what I need to do is subtract 5 from both sides. If I do that, then I get 2x equals negative 7. And finally, dividing both sides by 2 gives me x equal negative 7 halves. Over here, I also need to subtract 5 from both sides. That gives me 2x equals negative 3. And then if I divide both sides here by 2, I get x equals negative 3 halves. Now, if we recall that I'm sorry, that's not a negative. Yeah, it is a negative. Sure is. Okay. Now, if we recall here that negative 7 halves equals negative 3.5, and negative 3 halves equals negative 1.5, we can go back and remember or recall that the values we got off the calculator were the same. So we found this solution 3 different ways. We should feel fairly confident that we got it right. Now, when we deal with equations with two inequalities, it can seem a little bit trickier, but we can actually use a similar idea that we used in the previous example. And the way we do this is using this following property. When we have the absolute value of ax plus b equals the absolute value of cx plus d, that's equivalent to ax plus b equal cx plus d, or ax plus b equal negative cx plus d. We can use this idea to solve or to do the following problem. Here we're asked to solve the absolute value equation. Absolute value 2x minus 9 equals the absolute value of 8 minus 3x. Now, the first thing we need to do here is remove these absolute value bars. And so what I can do is say 2x minus 9 equals 8 minus 3x, or 2x minus 9 equals negative quantity 8 minus 3x. Okay, and now what I do is I solve each of these equations. Let's start over here. We need to get the x's all on one side, so I can add 3x to both sides. It gives me 5x over here. Minus 9 equals 8. Now if I add 9 to both sides, I get 5x equals 17. And finally, dividing both sides by 5 gives me x equal 17/5. Now on this side, the first thing I need to do here is distribute that negative. So we'd have 2x minus 9 equals negative 8 plus 3x. And again, I want to get all the x's on one side, so I'll subtract 3x from both sides. That gives me negative x minus 9 equals negative 8. Adding 9 to both sides gives me negative x equal 1. And then multiplying both sides by negative 1 gives me x equal negative 1. And so in this case, there are two solutions, x equal 17/5 and x equal negative 1. Okay, now we've been dealing with absolute value equations. Now let's see what we'll do when we have an absolute value inequality. If we let the solutions to the absolute value of ax plus b equal k be s1 and s2, where s1 is less than s2 and k is greater than 0, then we have these two situations. First, if we have the absolute value of ax plus b less than k, then this is equivalent to s1 less than x less than s2. If we have the absolute value of ax plus b greater than k, this is equivalent to the absolute value, equivalent to x less than s1 or x greater than s2. We can write similar statements for both of these when we're dealing with a less than or equal to or a greater than or equal to. So let's take a look at an example. Here we're asked to solve the inequality symbolically, and we have the absolute value of x minus 1 less than 3. Now, what we can do is remove the absolute value bars here by saying that negative 3 is less than x minus 1, which is less than 3. And now I can solve this by adding 1 to each part of the inequality. So negative 3 plus 1 is negative 2, and negative 1 plus 1 is 0, so that leaves me with x, and 3 plus 1 is 4, and so this would be the solution of this equation. Now, in the next example, we're asked to solve the inequality and write the solution in interval notation. And we have the absolute value of negative 3x plus 8 is greater than or equal to 3. So in this case, what we have to do, again, is get rid of the negative, or the absolute value bars. And we can do that by writing this as negative 3x plus 8 less than or equal to negative 3, or negative 3x plus 8 greater than or equal to 3. And then we can solve it as follows. We'll isolate x on one side, so we need to subtract 8 from both sides. So we have negative 3x less than or equal to negative 11. And then we need to divide both sides by negative 3. And don't forget, we have to reverse the direction of that inequality when we do that. And that would give us negative 11 divided by negative 3 is 11/3. Over here, when we subtract 8 from both sides, we get negative 3x greater than or equal to negative 5, and again, dividing both sides by negative 3, reversing that inequality, we have negative 5 divided by negative 3, which is 5/3. Now, in interval notation, this solution would look like this. It would be open for negative infinity up to 5/3. Now, since we're dealing with less than or equal to here, I need to use a close bracket there. Union close bracket, because again, I'm going to start at 11/3 on this side, and I have a greater than or equal to there, and that goes up to infinity. Now, we can also check this solution graphically using our graphing calculator. So I'm going to enter the two sides of the inequality on my calculator. So first I'll put in the absolute value of negative 3x plus 8, and the other part of it, of the inequality, is 3. And so what I'll do is I'll graph these two parts of the inequality together, see what that looks like. Now, when we look at that inequality, we know that we want the absolute value part to be greater than or equal to 3. And so we're looking for the parts of the graph where the absolute value graph is above the line. Now, we want to find those intersection points. So we'll go and use the intersect feature in the calculator. There's the first curve. There's the second curve. I'll move the cursor over there and press enter. Now, for that x value, I get x equal 1.6 repeating, and that's equivalent to 5/3. So that verifies the left interval in our interval notation solution. Now we'll find that other intersection, second trace, and then go down to intersect. And let's see, there's my first curve. We'll press enter, and then move it over close to the intersection point, press enter again. And that tells me the intersection is 3.6 repeating, and that's equivalent to 11/3. And so again, since we're looking for the part of the graph where the absolute value is above the line, then the solution would be any x value greater than 11/3. And that also verifies our solution. Well, in this section, you've learned about piecewise functions, and you've learned about some specific piecewise functions that are very important. And one of them was absolute value, and we've done a lot with absolute value inequalities and absolute value equations. Now, these principles are very important, and they'll come up again in future sections. So be sure to do some examples from your text, and I'll see you next time.